Okay, so I want to discuss again the addition of an acid such as HBr over a carbon-carbon double bond, and to look at this from a mechanistic point of view. What I have drawn out here is propene. This is the Lewis structure of propene, and here's the line diagram for this. Now we're going to be using the Lewis structure just to really look very carefully at what is happening to all the electrons in this molecule as the reaction occurs. But to be perfectly honest, Lewis structures for me are more complicated and more difficult to understand. When I look at it like this, I like to look at structures like this. This for me is a lot easier and simpler to make sense of. However, you have to understand where all the electrons are in order to understand these reactions. Otherwise, you're likely to make a mistake if you, as you're coming to grips with this. I have a lot of electrons drawn around here. I think we're just going to highlight certain ones to indicate the differences. For instance, these ones over here are lone pair electrons, and we'll color those in yellow there. I'm going to then take a green highlighter and you see the whoops, the green's not so good. So it's pink. All right. The pink over here is to highlight sigma bonds, and so we can highlight all these electrons or sigma. I'm going to do those two, and then the pi bonds I'm going to highlight in green. Sorry about those ones over there. Okay. All right, so each of those represents, those two electrons represents a bond, and these are sigma bonds, these ones which are in pink. So over here, this carbon-carbon bond over here, it's a double bond, consists of a sigma bond and a pi bond. It's the pi electrons which we're going to be interested in, and we're going to look at in terms of this reaction. And then we have all the other electrons around, and they satisfy the octets around each of the atoms. So what's going to happen in this reaction is that the pi electrons are actually nucleophilic. And that's one of the interesting things about pi electrons between two carbon bonds, is they can be nucleophilic if the right electrophile is around. In this case, hydrogen, or Bronsted acid, is a good electrophile. So these get to act as the nucleophile, and the proton is going to act as the electrophile. So what's going to happen in this reaction is that these pi electrons over here are going to move up and donate to this proton over there. All right, this is the movement of those electrons. Now, as those electrons move up to connect to this proton over there, the proton can only form one bond. So as these connect to the proton, these electrons which are connecting the proton and the bromine together need to leave and break away from this proton. So they're going to break away and end up on the bromine. So essentially this whole bit here, okay, if I could animate this, moves off in that direction over there. So that's going to move away, and these are going to connect to the H. Now what you need to consider is that at the moment these two carbon atoms are sharing these electrons. As these electrons are given to the proton, they cannot be shared any longer between the two carbons, and so the protons neither, as they go to share to this proton over there, as those electrons go, those electrons are going to move over to either this carbon over here, or they're going to move over to this carbon over here and share to that proton. So we have two kind of pathways that this reaction can undergo. And so if I draw those out, the net result of those pathways, forgive me for drawing this Lewis structure a bit funny like that. Okay, so we draw everything in, connecting all the H's, and we're going to put the H here on this one. All right. So if we have sigma bonds everywhere. Sigma, 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 sigma. All of these are sigma bonds. No longer have any pi bonds. The H that was over there is now ended up on this carbon, and this carbon over here only has 1, 2, 3, 4, 5, 6 electrons around it, so it's missing 1 in terms of its charge, and so it is positive. It is a carbocation. If these electrons, as they were given to the H, ended up on this carbon over there, then we would end up with the molecule in terms of its Lewis structure. Oh, mistake. Those are not there. Looking like this. And so the H is there, and these are the other ones that want it in the first place. So we have sigma, 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 sigma bonds everywhere. And this one is only got 6 electrons around it. 1, 2, 3, 4, 5, 6. If we add it all up, work out its charge, we'll see that this is positive. It's a carbocation. So these are the two options. During this reaction, as the pi electrons are being given to this proton, depending on which side the proton ends up on, depends whether we get a carbocation that looks like this, which is a primary carbocation, or we're going to end up with a carbon over here, which is a carbocation there, which is a secondary carbocation. It's a primary carbocation because the carbon with a plus on it is bonded to only one carbon. It's a secondary carbocation here because the carbon with a plus on it is bonded to 2 carbons. A tertiary one would be bonded to 3 carbons. The higher the degree of substitution, the more stable the carbocation is. So during this reaction, in the transition state, as these pi electrons are adding to this proton, what is occurring is that the molecule has a choice of where these electrons end up on. And when they end up on this carbon, we end up with a secondary carbocation. When they end up on this carbon, we end up with a primary carbocation. So during the reaction, the choice is actually going to favor this one being formed because it is more stable. And so there's going to be a natural push for those electrons to end up on this carbon over here, and so form a secondary carbocation. So this is favored and will result in the major product. We forgot about the bromine, so the bromine disappeared, and these are our lone pair of electrons, and it is overall negatively charged, and now all of those are lone pairs. And what's going to happen is one of those lone pairs, doesn't matter which one we use, is going to add to this carbocation over there to satisfy the octet rule, and so we will end up, and now forgive me, but I'm just going to draw out the lines because it's getting a bit crazy, and we end up with this a brand new bond to the bromine. But of course, now what do we have? It's just sigma bonds everywhere. All right, and what I haven't drawn in, because I was a bit lazy, I'll put it now, is of course the bromine still has all those lone pairs of electrons, but it's no longer negative. Overall, this molecule is neutral. All right, so this is the long way of explaining the addition of HBr over a double bond. The key aspects to this, understanding this, is that in the addition step, the carbocation that forms, the more substituted carbocation is the preferred one, and so the halogen, all right, this bromine here, will end up on the carbon that is most substituted. So let's just go back to the starting material here in the line structure, and we see that we've got a carbon-carbon double bond. This carbon is connected to one carbon. This carbon is connected to 2 carbons. So this carbon is the most substituted double bond, and that means that the bromine, when we add HBr over this double bond, is going to end up over there. And the rule, the name of the rule that decides that, it talks about that, is Markovnikov. Markovnikov's rule. And you need to know that. All right. That's the rule that we use to decide what will be the major product of our reaction. All right. So this will be the major product. The minor product will be the one where it adds to the primary carbocation of this reaction. Okay, so that's the basics for the mechanism of this. However, if we're going to do this in reality, if we're going to show this, we cannot be drawing out these Lewis structures like this. It's going to take far too long. And we really do need to move to using just the skeletal structures. And so an adequate mechanism for this particular reaction that we've shown is to draw out this propene, all right, 3 carbon with an alkene on it, and we show our H, Br, and the pi bond is going to pick up that proton, and this bond here between the H and the Br is going to break. Notice that there's a flow of electrons. These electrons which are in this bond, which was that pi bond, I'll even highlight it here, color, are going to flow in to pick up the proton, and in so doing, this bond over here, which was a sigma bond, is going to break and end up on the bromine. Right, so our first intermediate is the carbocation, which is going to look like that. I'm not showing the hydrogen that bonded to this carbon because in skeletal structures we don't show hydrogens. All right, so we just need to become comfortable with that and realize that this carbon over here does already have 1 hydrogen on it, all right, but it's only got 3 bonds to it, so it's now a carbocation. You must be able to see that, all right? If you're not able to see that, you've got to go back to this and recognize that that over here, this monstrosity of Lewis structures and electrons, is actually the same as the skeletal structure over here. And then lastly, we just need the Br minus, which is in a lone pair, to add to that, and our major product looks like this. Okay, so that's the basics of doing these sorts of reactions, the addition of HBr to a carbon-carbon double bond. You will need to do many examples just to get a feel for this, and so as a suggestion, why not practice doing this mechanism on this cyclopentene over here, and I'm going to put a methyl group there in order to help you think about the 2 different products. So take that, react it with HBr, and work out the mechanism for that. Not just show what the product should be, but actually work out those mechanisms as a way of practicing. Okay.